All right, now we start actual calculus work. In this first section in chapter 3, chapter 3 deals with derivatives. We're now introducing the first half of calculus 1, derivatives. And we'll define what that means in a second. Section 1 deals with tangent lines and the derivative at a point. Because if you look at most of the stuff that we've been dealing with since day 1, has been the slope. We went from the algebraic definition to the function definition, in section 1, we talked about slopes, we talked about rates of change. And they're both the same thing. And then we moved on further because that definition of slope only worked for linear equations. Where we had a straight line. But what we want to get to is we want to be able to find the slope of a curve at any one point. So far, because we've seen all these other definitions of slope required us to look at a secant line where it crosses the graph at 2 points, where we have x1 and x2. Because what we want is we want to know what the slope is at that one point. And that, with respect to the rate of change, was called the instantaneous rate of change. We want to know what's happening at that one point, at that one piece of part of time. We defined the distance between our 2 points of the secant line as h. And algebraically, the way it was figured out was we moved, since we want to know what this point is, we took this value and moved it closer. So then at each point, that secant line was getting more and more and more and more like the graph we want to look at, the slope of the graph we want to look at. So eventually there's only one slope, one line that touches that curve at one point. And that's called the tangent line. So in this chapter, we're going to take the stuff we did in chapter 1, all that stuff we did in chapter 2, and we're going to start putting them all together. We started that process. We have to go further with this, the slope. Because remember, we only want the slope of a point at a single location on that curve. So we know that x1 plus h equals x2. If I start at x1, add h to it, I go to x2. Which means that x1 is actually x2 minus h. So for looking at our equation, which we had earlier in the slope, x2 was x1 plus h minus f of x1. And let's look at this one. Forget that. So if h was actually x2 minus x1, if we solve for h, which means our difference on the bottom was h. That was called the difference quotient. That found the slope at one point. If we knew what h was. That's what we did in chapter 1. In chapter 2, we talked about limits. So what we're looking at here is what would be the limit as x2 goes to x1. In other words, as h, the distance between them as it goes to 0. So if we look at the limit as h goes to 0 of our difference quotient, what that finds for us the slope of the line tangent to the curve at any point. Which means that we found the instantaneous rate of change at any point. So this limit function, the rate of change, is is the slope of the tangent line at any given point. Let's look at example 1. Sample 1. We have a couple of parts. Find the slope of the curve y equals 1 over x at any point x equals a, as long as a is not equal to 0. You guys should have this on your sheets I gave out last week. What is the slope at x equals -1? Where does it equal -1/4? And then what happens to the tangent line at a 1 over a as a changes? Right. So let's look at the first part. First one, find the slope at any point that x not equals 0. So it's looking for the slope, which is the limit as h goes to 0 of x plus h minus f of x over h. And our function is 1 over x. So what do we have to do first? To use this formula, we have f of x. Do we have f of x plus h? No, we have to find an f of x plus h. Because now we could just plug and play. The limit as h approaches 0 of 1 over x plus h minus 1 over x over h. Remember, it's asking us to do what? It says find the slope of this function at any point x equals a. So anywhere we see an x, what do we put in its place? A. This is saying when x equals a. So we have to algebraically, remember I told you first day of class, calculus is only the first step. This is all calculus. The rest of this is algebra. How do we subtract the two fractions on top? We need to have a common denominator. So this one needs an A over A. This one needs an A plus H over A plus H. A times 1 is A minus 1 times A plus H. Limit as H approaches 0. We have A plus H. This negative goes inside there. Distribute that negative. The A's cancel, so we have a negative H on top. Since we have a fraction over a fraction, take the top fraction, leave it alone. Multiply by the flip of the bottom. The H's cancel. So we have on top -1. On the bottom, we have A plus H. H goes to 0. So we have -1 over A times A, which equals -1 over A squared. The second part of question A says, what is the slope when x equals -1? So with this was all found out. So the slope is actually -1 over x squared. Because remember, we said that x equals a. So if we put -1 in place of x, what do we get? When x equals -1, the slope becomes -1 over 1, which is -1. Where does it equal? What was that? -1/4. Remember, when it's asked where does it equal -1/4, what exactly is it looking for? What does this number represent? Yeah, Yeah, it's the slope. Where does the slope equal -1/4, which is -1/x²? To solve for x, the only way those can be equal is if 4 equals x², square root both sides, x equals what? Plus or minus 2. Yeah, because whenever you take a square root of something squared, it has to be plus or minus. Let's see what this really means. The graph of 1/x looks like what? When x goes to infinity, where does it go? Where does y go? No. Think about it. When the bottom number gets bigger, what happens to the whole number? It gets bigger or smaller? It gets smaller. So the larger it gets smaller, 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 eventually goes towards 0. So the graph looks something like this. For the bottom side, for the positive side. And it looks something like this for the negative side. So what it said, when x is 1, y is 1. When x is 2, y is 1/4. I'm talking about the slopes. So this is, so it's a negative slope because it's going down. At this one, it's a negative slope because it's going down. Likewise, on the other side. So the slopes of these two lines at -2 and 2 are parallel. What was the third one asking? So the question is, so where does it equal -1/2? It equals at plus or minus 2. What happens to the tangent line as A changes? What happens to the tangent line at A 1/A as A changes? Let's look at the graph again. The graph looks like this. The graph looks like this. What do we notice about the slope of that curve? The function is 1/x, and the slope is -1/x². So what do we notice about that? The curve, the slope of that curve. It's always going to be what? It's always going to be negative. Because no matter what you put in there for x, when you square it, it becomes positive. It's going to turn out negative. So it's always a downward, but it goes from near horizontal to near vertical. because it's got a horizontal asymptote at 0, and it's got a vertical asymptote at x equals 0. Think of what we did yesterday. How do we find the horizontal asymptote? You look at the degrees. Ideally, okay, that's the algebra. In calculus, we're supposed to find it the limit as x goes to infinity. As x goes to infinity, 1 over x goes to 0. As x goes to positive or negative infinity. So that's your horizontal asymptote. How do you find the vertical asymptote? That's the algebra part. But since our only point in question as x equals 0, what happens as we go to 0 from the left? What happens when we go to 0 from the right? What are the limits? As we go to 0 from the left, it goes to negative infinity. As it goes to 0 from the right, it goes to positive infinity. Yeah, the algebra part just tells us where they are. The calculus part tells us what happens as the graph gets closer to it. Because if we understand the calculus part of it, then we could draw any graph we want to if we know the horizontal and vertical asymptotes. What happens as they approach those values? Do we have example 2? No. So any questions so far? So now we're going to look at rates of change as a derivative at a point. Here we are. We finally get to do something calculus-y. The derivative represents the slope of a curve at any point x on the curve. Does that definition look familiar? The slope of a curve. In other words, it's the slope of the tangent line at any point on the curve. Does that definition sound familiar? Just did that. As h goes to 0. The difference quotient. That's the definition. So now we have to give it a symbol because it dealt with the functions. There is the representation of a derivative. It's the function first prime. That's called f prime of x. That's how you read it. Here's the next example. Okay, is the derivative just doesn't mean slope. It does mean rate of change. Rate of change means different things. In business, what do you call the rate of change of something there? No, because you use slope. If you're dealing in business, you're talking about production costs, revenue. You're looking for profit. Because if you think about it, in business, the cost function, the cost of how many items you're going to produce, the revenue of how many things you're going to sell. The profit is your revenue minus your cost. These are all functions with the number of objects you produce. There is no slope because the stuff you produce isn't on a slope. It's the physical number. In business, we don't call them rate of change of slope. We call them marginals. The marginal cost, the marginal revenue, the marginal profit. Those each, that the term of saying marginal simply means that you're taking the derivative of that function. What is the rate of change of that function depending on how many items we produce? In physics, derivatives have some more meanings, which we're going to be looking at in this chapter. As things move. The position of an object as it moves through space is represented by S of t. What happens when that thing picks up speed? This is the position of any place. The change of position is called the velocity of an object. Well, the velocity is the rate of change of the position, so it's the first derivative of that object. Well, what's acceleration? Acceleration is the change of your velocity, which means, since that's the first derivative of velocity, that means it's the second derivative of your position function. Well, what do you call the change of acceleration? That's called the jerk. So the change of acceleration is called the jerk, which means it's the next derivative of your velocity, which means it's the third derivative of your position. As long as the function is defined, we can keep on finding a whole bunch of different definitions of this stuff. There's no limit to the number of derivatives you can take. For example, the sine and cosine. There's never an end of sine and cosines. So the derivatives find us rates of change, the slope of the tangent line at a curve. Here's example 2. This is a free falling one. We studied the speed of a rock falling freely from rest near the Earth's surface. The rock fell, this is example 2. The rock fell at 16 feet per second during the first t seconds. And we use a sequence of average rate of change in shorter intervals to find the instantaneous rate. What is the rock's exact speed at what is the rock's exact speed at t equals 1. So what it's looking for, since it's looking for speed, speed is the change of position of an object. So what we're looking for here is the 16 t, which is t plus h squared minus 16t squared over h as h goes to 0. So we're looking at the speed. We're looking at the change of position over time. So what is t? We're looking at t equals 1. The limit as h approaches 0 of 16, 1 plus h squared minus 16, 1 squared over h. We have to FOIL this one. 1 plus h times 1 plus h is 1 plus 2h plus h squared minus 16 times 1. That's what 1 squared is. All over h. Limit as h goes to 0. Distribute that. So on top we got 16 plus 32h plus 16h squared minus 16 over h. Combine like terms, the 16 minus 16. So we have 32h plus 16h squared over h. We can factor out an h on top. So we got 32 plus 16h over h. H's cancel. The limit as h approaches 0 of 32 plus 16h. The h goes to 0, so we're left with 32. The question asks, what is the rock exact speed? It is 32 feet per second. It is exact speed at t equals 1 is 32 feet per second. So far, so good. So we're using the limit function, the difference quotient, to find the derivative. Now we're going to switch over and find the derivative using formulas. Stop here.